Class of Calculus 3, and we are talking about triple integrals in cylindrical coordinates. And this is in general how we evaluate triple integral in cylindrical coordinates. It is in the form in our order for r, dr, d theta, dz. Keep in mind this r, dr, d theta, dz, it is used to replace dv. And r, dr, d theta, hopefully it's not too strange to us if you worked very hard on double integrals, and if you know very well about polar coordinates, it's the same kind of thing. Cylindrical coordinates, they are derived directly from polar coordinates. And also the interesting thing was to note here is we said a triple integral can be evaluated in 6 different ways. And indeed, it is just true. Even with cylindrical coordinates, the triple integral still can be evaluated in 6 different ways, because we do have dr, d theta, dz. And indeed, the example we did, okay, it is different in a different order, because if you look at the description we generated for the solid, as you can tell, z depends on r, so it really says z should be evaluated first, then r. So this is what I did. It is r dz, then dr d theta. Somewhat theta and r, they are independent, so it really doesn't matter. You can evaluate them separately or evaluate the integral into r and theta simultaneously. And so this is the example we already finished. And it is about the triple integral in polar coordinates. And mostly for this part, I want to talk briefly triple integral in spherical coordinates. Okay, rectangular coordinates, we use the order of the triple x, y, and z. For cylindrical coordinates, we use r, theta, and z. Then for spherical coordinates, we have somewhat a notation a little different. Rho, theta, and phi. Rho, it is the distance from the point to the origin directly in the space. Theta, it has the same meaning as in polar coordinates. Phi, it is the angle from the line connecting the point to the origin to the z-axis. That's the phi. And well, certainly you want to know the conversion of polar coordinates, spherical coordinates and the rectangular coordinates very well. Specifically, one big important property about spherical coordinates is x squared plus y squared plus z squared equals rho squared. I think we are going to use this result in our calculation for the integral. Okay. And also there are some common shaped surfaces and regions in spherical coordinates, Hopefully that will be helpful to just for reviewing purpose. And also actually they will be very helpful. You can imagine how the solid would look like when we evaluate double integral. And then the real question is, how do we evaluate a triple integral in spherical coordinates? So this is the formal arrangement. It's kind of getting long. I suppose this is the way how we denote a regular triple integral. Then we evaluate the triple integral using spherical coordinates. Everything will have to be changed in terms of rho, theta, and phi. Okay, so x is rho sine theta cosine phi. Y is rho sine phi sine theta. And z, it is rho times cosine phi. And then like we did for cylindrical coordinates, remember we have the extra r for dr d theta. And indeed, we do have similar arrangement for spherical coordinates. You always need to have this extra rho squared sine phi for d rho d phi, and then d theta here. You always need to have this extra part, rho squared sine phi, not only just d rho, d phi, d theta. You need to add this extra part for the triple integral in spherical coordinates. So I have one example over here. It is from the textbook 5.51. It is to evaluate a triple integral. And you may want to say everything is given. Why make it that complicated? Why making it that complicated? And if you think very carefully, this triple integral, somewhat it is related to the problem we did in the same section. And really, this triple integral we are working on here, it is a triple integral over a solid, such that the lower part of the solid, it is the cone-shaped surface. The upper portion, this time it is no longer the paraboloid anymore, it's the sphere. And also, I'm seeing the y-coordinate has to be positive, which really means y-coordinate will have to be positive, which really means along the y-axis, let's consider along the xy plane, the entire surface will have to be above the y-axis. And the z is also positive. Z is also positive, okay? And x is also positive. Indeed, x, it is only running from 0 to 3. So really, we are only looking at the solid in the first octant. Okay. So this is according to my understanding of the surface of the solid in the xy plane, and this is the spherical coordinates for the solid. And the rho is changing from 0 to 3 times square root of 2, and you want to take a look how I get this 3 times square root of 2, okay? And the theta is changing from 0 to pi over 2. I think we mentioned that y has to be positive and x has to be positive. So whatever the solid we may have, it really will have to reside the part in the first octant first. Okay. And then for the angle, it is not going 0 to pi. It is going from 0 to pi 4 only, pi over 4 only. And then we convert this triple integral using the spherical coordinates. And don't forget, x squared plus y squared plus z squared, it is replaced with rho squared. And then this dz, dy, dx part, it is replaced with rho squared sine phi. This is the actual part, right? Then d rho, d theta, d phi. And rho, as indicated in the beginning, is changing from 0 to 3 times square root of 2. And the theta, it is changing from 0 to pi over 2. And the phi, it is changing from 0 to pi over 4. So rho to the 4, I have the antiderivative of the 1/5 of rho to the 5. And then sine phi, theta and the phi, I hope you see they are independent. So you could evaluate those two integrals separately. That's what I did. And antiderivative sine phi, that's negative cosine phi. Theta, antiderivative constant times theta is just theta. Okay. Phi is running from 0 to pi over 4. Theta is running from 0 to pi over 2. So in the end, did I finish this number? Probably I did not finish this number here. I think I just want to make sure I show all the work correctly. I think this is the work I have, and I hope it does explain the idea how how we evaluate a triple integral using spherical coordinates, and especially if you have spheres involved. And usually it is easy to evaluate a triple integral using spherical coordinates. So this is the material in section 5.5, cylindrical and spherical coordinates with triple integrals. Thank you for watching.